Okay.
Okay.
Now we enter into the zone of random mismatch. Now look at this image. On the left side is one cross-section view of a transistor, and on the right side is the dopant profile, which is particularized. Okay. The red ones are donors, the blue ones are acceptors. Okay. Now what happens? Let us say you scale down. You scale down the technology and you expected 20. So this was your gate region. So this was your gate region. And you expected 20 dopants over here beneath the gate. Okay. But in reality, just give me a minute. In reality, there were, let us say, 3 extra dopants. All of a sudden, what happens? The contours, the potential contours of this gate device will be different from the device that you had designed it to be. You will now need more band bending. Are you able to see this? To get to the VT of the device, you will need more band bending, and therefore you may end up as a high VT device. A VT is slightly higher than the regular device that you had intended it to be. It can also happen that instead of 20, there are 18 dopants. Now, less band bending is required for VT to be there, and therefore you will see that the device is a little fast. Are you with me?
So, sir, this is random.
This is random. Two adjacent devices, structurally matched, WP is same, stress is same, everything else is same. Even then, you cannot control how many dopants will be there beneath your gate. It is physically not possible. So such variations, which you cannot really model deterministically, you model them statistically. You say that, okay, of 100 devices, 70 devices would have 20 dopants only. Now 10 devices will have 22 dopants. 10 devices would have 18 dopants. Then remaining 5 devices would have 25 dopants. And another 5 devices would have 15 dopants. And you say that there is a distribution. There is a distribution where some devices are faster, some devices are slower. Are you able to see this?
Sir, I have two questions. So one is why this process, why is this random, sir? I mean,
You tell me. I
sir,
want to bombard 20 dopants in a region which is, let us say, 1 micron by 65 nanometers.
so 1 micron by
1 micron device with
okay.
minimum length.
Yes.
So 65 nanometer into 1 micron. In that region, I want to bombard 20 dopants. Can I bombard 20 dopants exactly? Or sometimes there will be 21, sometimes there will be 19. It's a process, no? It's a natural process.
Yes, sir.
You're not placing dopants one by one. You're just bombarding and you're letting them diffuse. There are
Yes.
bound to be variations.
So, but the machinery which I'm bombarding, I have the frequency, everything I have in control, right? So I can be sure ki how much I'm
So you
bombarding.
have, so okay, let us do this experiment again, Raghav. You have a pencil with you? Pen, paper, pencil with you? Something like that?
Yes, sir.
You have control over your hand?
Mm.
It is the same pencil that I want you to write your name with 20 times. And it has to be exactly the same.
Yes, sir. Okay.
Can it be exactly the same?
No, no, sir.
No. Why?
Perfect is not there. Perfection cannot be
It
100%
is a
perfect.
natural process.
Yeah.
It is a natural process. There are bound to be some variations. The 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 velocity of devices, the velocity of dopant atoms that you are sending, that you are bombarding, that is going to be not normally distributed, yeah.
Hmm. Yes, sir.
है ना? So there is no way you can have them exactly the same under every device. And you cannot model this. You can only statistically model this. So statistical models would appear, but exact models you cannot have. To do the worst case analysis, you may say that, okay, I have to assume pass gate to be at 3.5 sigma, pull down to be at 4 sigma away. And that is my worst case. That was what we did in this S&M analysis. That was what we did in the right margin analysis also in the previous lecture. So we placed devices at the worst places and we saw the impact. But it is not that this is bound to happen exactly this way. We just want to be sure that statistically we are safe.
So when you say कि statistically determined, you say कि आपने जैसे बताया कि 100 में से 70 इतना होगा, 20 का इतना होगा, but I cannot locate कि which exactly device ये variation होंगे.
Yes, that you cannot tell. 100 में से 70 होंगे, but which 70, the first 70 or somewhere randomly distributed 70, that we cannot say.
Okay. और सर मतलब जैसे डैंड आपने डोपेंट का यहाँ पे एग्जांपल दिया, तो हमने वर्स्ट केस की डोपेंट भी कुछ होगा, सो उसमें भी कुछ डिवाइसेस आ रहे होंगे, बट हम
Yeah.
सारे डिवाइसेस को उस कर्व में इसी पॉइंट पे क्वालिफाई करने की कोशिश करेंगे.
No,
तो
no, 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 no. That is where we did that. Na? We said this is my distribution. And we said, let me put pass gate at minus 3 sigma. Let me put pull up at plus 3 sigma. You remember? We did that. So we did not say कि सारे devices एक ही जगह पे हैं. We actually, for verification, for designing, we actually put devices at different corners. And that was when we did it.
राइट. आई मीन सब पास गेट का जो हमारा वर्स्ट पॉइंट होगा, वहां पे सारे पास गेट का एनालिसिस वहीं पे करेंगे हम, मतलब सिमिलर काइंड ऑफ डिवाइसेस का.
जो भी उस सिस्टम के लिए, at times pass gate का lowest VT is what you desire. At other times pass gate का highest VT is what you desire.
ओके.
For S&M analysis, you want low VT on the pass gate. For right time analysis or right margin analysis, you need high VT on the pass gate.
यस सर.
So at times you will use one side of the curve. At another time you will use another side of the curve. Okay.
Sir,
Yes.
sir, can you come back one slide? So, sir, this according to this below graph, sir. So this dopant fluctuation is the major cause to the VTH variation.
Yes.
And sir, one thing also I want to ask, sir, at lower technology nodes, मतलब सर कम चैनल लेंथ पे, तो सर ये हम लोग का जो जैसे आपने बोला था कि जो हम लोग का सिग्मा शिफ्ट आएगा वो बढ़ता जाएगा.
Yes. That is what is shown in this curve.
Yes, sir. Okay, sir.
Okay. So again, this is about the impact it has on the memory cell. So this is actually the memory cell ka S&M analysis only, where we say that, okay, for different S&M values, how is the distribution when cell ratio is moved from 2 to 3 to 4? Okay. And this has considered only the random dopant fluctuations as a part of variations as yet. Other random things are not put in picture. Another random effect is interface roughness. What does that mean? See, finally, you grow silicon dioxide, let us say. At some places, there are 3 atoms of 3 molecules of silicon dioxide. At other places, there are 4 molecules of silicon dioxide. At some places, a molecule is placed in a particular manner. At other places, the molecule is placed in a different manner. So what happens? The thickness of silicon dioxide can vary across the gate region. Some places it is 2.2 nanometer wide thick, at some places 2.6 nanometer thick, at some other places 2.4 nanometers thick. So what does this mean? That even though you said that your gate is 22 nanometer thick or 25 nanometer thick, there are variations around it. The gate oxide thickness is not exactly the same. Due to this, some devices will operate fast, some devices will operate slow. Adjacent devices both have average thickness of 25 nanometer only, 25 angstroms only. But in one device, it was more towards 24. In the other device, it was more towards 26. And it is random. You cannot control it. Are you with me?
Yes, sir.
So this again is a random variation which you have to model in your Monte Carlo simulations. Another random variation is line edge roughness. What does line edge roughness mean? Line edge roughness means that you wanted to design a poly which is of one particular width throughout. Whereas poly in itself is a polycrystalline material. So there are crystals there. And when you will do etching, when you will do chemical etching or anything, you remember that crystals have anisotropic behavior. They behave differently across different directions. So there is a crystal which is placed here and a crystal which is placed here. So when you do the etching, what happens? So let us take this example. Let us say that there are these different crystals of silicon dioxide that form the poly region over here. And so on. So when you started to etch, what happens? The crystal boundaries, at the crystal boundaries, the extent of etch changes. So finally, you may have a polysilicon line. So you wanted it to be completely straight and parallel. Finally, you will have a polysilicon line which could be like this. Thicker somewhere, thin somewhere, and so on. You notice in this image, the poly thickness is not constant throughout. What does this mean? This means that the length, effective length, is changing. Now let us say there was a contact over here. And in another device, there was a contact over here. The effective thickness of the gate for transmission of current from source to drain, from one contact to the other, is going to be different for every device. Are you able to see this?
Sir? Sir, how is the thickness changing? I mean, along the line it is changing, na? So thickness so remains will same, right?
So
it is along the edge.
thickness, I mean, okay, let me not use the word thickness. Let us use the word width. The length of your device is changing. Are you able to see this? Now, the length of the device is changing differently for different devices because of this line edge roughness.
Also, sir, it seems that in the same device, the length is not constant throughout.
That is also the case. But there will be average length. So average length may still be 65 nanometers, let us say. Okay, average length is 65 nanometers, but because of line edge roughness effect, the current flow which was happening from one contact to the other, the effective gate oxide thickness would be different. The effective poly length, the gate length would be different. There will be variations there.
Sir, it is written that LER is independent of gate length. So,
Yes.
sir, how it is causing variation, sir?
LER is independent of gate length, but it does not say that LER doesn't happen.
Yes, sir.
If LER is happening, do you realize that gate length is effectively changing?
Yes, sir. Yes, sir.
What it means that it is independent of gate length means that it is dependent on polycrystalline, the size of your crystals in the polysilicon, not on the length of your gate. Whether it is 1 micron wide length or it is 65 nanometer length,
Yes.
the variation will always be plus minus 3 nanometers.
Okay, sir.
That is what it means by this statement. It is
Okay,
not
sir.
a percentage
So,
variation.
sir, if it is dependent on the crystalline this thing, so sir, if with the same crystal we are manufacturing 65 nanometer, and then we are moving down in lower technology nodes. So, sir, this thing will be, sir, constant, na? This LER in every technology node.
LER will be constant, but let us say there was a 65 nanometer technology.
Yes,
Because
sir.
of this plus minus 3, what is the fastest or what is the minimum length that you will get? 62?
Yes, sir.
62 versus 65, what is the percentage difference?
Uh,
Something like 5%.
yes, sir.
Now let us come to 20 nanometer technology.
Then it will cause, yes, at lower technology node, then it will be significant.
The impact is much more.
Yes, sir.
The
Okay,
difference is now around 15%.
Means, sir, this LER will be same across every the channel length, but it will be more significant in lower technology nodes.
Not just lower technology nodes, in the same technology node, if you use minimum length, the impact is more.
Yes, sir. Yes.
Why lower technology? Lower technology node is a different technology. You actually use a different material.
Yes,
You
sir.
could use a finer, more granular polysilicon.
So, sir, for removing this crystals, we can use, sir, we can be more precise during making these. So we can use lower wavelengths to manufacture. So we can avoid this LER.
Do you use wavelengths to manufacture?
Sorry, sir. Sir, we studied that in that, sir, sir, that optical OPE, sir.
So do you remove it through OPC?
No, sir, but we can avoid.
How does removal of how does removal happen finally?
No, sir, removal. We can avoid this polycrystals, sir. So that we may avoid LER, sir.
So you will not use polysilicon then. What will you use?
So, सर जैसे कि सर उसको अवॉइड नहीं कर सकते हैं क्या जो क्रिस्टल्स
आप
हैं
बताओ ना, आपने, मैं आपका आइडिया सुनना चाह रहा हूँ रजनीश, आप क्या कह रहे हो, मेरे को समझ में नहीं आया.
सर आई वाज जस्ट आस्किंग सर if we could avoid this सर एक्स्ट्रा जो रफ एजेस आ रहे हैं सर, इनको अगर किसी तरह हम लोग अवॉइड कर लें सर, तो सर जो हम लोग का
देखो ये तो इच्छा मेरी भी है, सॉल्यूशन बताओ ना.
सॉल्यूशन सर हम लोग मतलब कोई लोअर वेवलेंथ यूज करें ताकि हम लोग का सर कम से कम ये एज रफनेस है.
तो वेवलेंथ से क्या होगा? मैं कैसे रिमूव करता हूँ इसको, पॉलीसिलिकन को? मैं एक मास्क बनाता हूँ, मैं उस मास्क को लाइट से इंजेक्ट करके हार्डन कर देता हूँ. अब रिमूव करने के लिए मैं क्या करता हूँ, मैं एसिड डालता हूँ. आई पुट एसिड देयर.
यस सर.
That acid reacts with polysilicon which is exposed and I wash it away.
Yes.
Now where does light come in here? There's a chemical reaction that is happening.
Yes, sir. Here it's not needed. Yes. Okay,
there's a chemical reaction that is happening, and that chemical reaction is anisotropic in nature because of the crystalline structure.
Okay, sir.
It's a physical process. It's a chemical process.
Yes, sir.
है ना?
Okay, sir. Yes.
Okay. Sir, the mask which you make, that will be making it with the help of the light, right? I think that's what he was mentioning before.
Yeah, and that is what I'm clarifying. It is not about the mask at all.
So if we
It is
make some
about the
kind of
process. It is about the process of etching. It is about the chemical removal of the polysilicon that was extra there, so that only polysilicon wires remain. It is about that.
yes. Okay.
That is what I'm clarifying.